Hello everyone, welcome to another episode from Chedexcel. Today we are going to talk about ionization energy values and the successive ionization energy values. So in this video I'm going to talk about both of them and I'll categorize what are the topics that I'm going to discuss at first, so you can get a rough idea, and I'll put the chapters as well, so you can easily watch what video or what part you have to understand mostly. And to get the whole idea, it's better to watch the entire video, but I put the chapters so you can get which part you want to mainly refer when I am talking about. So what I'm going to discuss first is I'll talk about what is the first ionization energy. Then I'll talk about how it changes from left to right of a period. Then how it changes from top to bottom of a group. Then the fourth one I'll be talking about why there is a difference between group 2 and group 3 for the first ionization energy. And then I'll be talking about difference between group 4, group 5 and group 6 in the first ionization energy. And then I will move into the successive ionization energy values, and there I'll be talking about the successive ionization energy value of sodium and why do we use the log values instead of the real values, and how we can figure it out group number by looking at the successive ionization energy graph, and what are the other details we can take from the successive ionization energy graph. Right, so that is the content like in this particular video. So I put them in the chapter wise as well, and you can refer them. Okay, so let's move to the first part, that is the first ionization energy. Now when we talk about the first ionization energy, so the first ionization energy is simply defined as the energy required to remove an electron from a gaseous atom to form a unipositive gaseous ion. Now gaseous atom to form gaseous ion, sodium gas, remove an electron to form Na plus gas, an electron. This is what we call as the first ionization energy. Now it can apply for a metal or an unmetal, Cl plus gas and electron. So the first ionization energy generally increases from left to right of a period. That's something you have to remember. The first ionization energy always increases generally from left to right of a period. So what are the reasons? They commonly are these. The reasons we say, from left to right of a period, electrons are filled to the same main energy level so that their shielding effect remains the same. Atomic radius decreases and the number of proton increases, so the nuclear attraction increases. Therefore, more energy is required to remove an electron. So those are the three common things, or those are the three main parts that we have to write when they ask why the first ionization energy generally increase from left to right of a period. Next one, the variation from top to bottom of a group. Always the first ionization energy decreases from top to bottom of a group. The reason is, down the group, new main energy level is added, so the shielding effect increases, nuclear attraction decreases, therefore less energy is required to remove an electron. So down the group, first ionization energy decreases. Now even though we say there's a general increase, when we draw a pattern or like a graph, we would see it comes like this. This is rough sketch how it goes. So here you will have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. That's how it normally happens. So in a group wise, this is group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8 or group 0. Again you can see this is group 1, this is group 2, this is group 3, this is group 4, this is group 5, this is group 6, group 7 and group 8. Right. So basically what happened down the group, you can say it increases, decreases, but always group 2 and group 3 there's a difference, group 5 and group 6 there's a difference. So we are going to look at what are the reasons that we have in these two. So we are going to look at why group 2 and group 3 is slightly different. Why group 3 is lower than group 2. Here also group 3 is lower than group 2. So there are certain things we'll see. Now when you talk about group 3 is lower than group 2, right? Let's say we take aluminium and magnesium. I am taking these two. Aluminium electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1. And magnesium is 12, 1s2, 2s2, 2p6, 3s. So the reason we say is this: for aluminium, electron is removed from a p subshell which is shielded by inner s subshell. But for magnesium, electron is removed from a s subshell which has less shielding effect compared to aluminum. That's the reason. That's what we always write. If I tell it again, for aluminium, electron is removed from a p subshell which is shielded by inner s subshell. But for magnesium, electron is removed from S subshell which has less shielding effect than aluminum. That's the reason. Now you can see here this p electron gets covered from S as well, but here it is only 2p. So it doesn't have it has less shielding effect than aluminum. So more energy is required for magnesium to remove. But again, after that, when it comes to silicon also electron removed from a 3p which is shielded more, but there are more protons, so greater nuclear attraction. So you can see that difference only within 2 and 3 and 5 and 6. Always 3 is lower than 2, but 4 is greater than 2. Yours the same. Right. That is the reason why group 3 is lower than group 2. Then they commonly ask why group 6 is lower than group 5. Or they can ask why sulfur has a lower first ionization energy than phosphorus. Or they have asked why oxygen has a lower first ionization than phosphorus. So in such situation, what is the reason? So if I write it again over here, so phosphorus 15, which is 1s2, 2s2, 2p6, right? 3s2, 3p3, sulfur 16, 1s2, 2s2, 2p6, 3s2, 3p6, 3p4. Now what happened here is, now we can't say that phosphorus has less shielding effect because both electrons are removed from 3p, so they have the same shielding effect. Now when you talk about the electronic arrangement, 3p3 means it has half filled stable electronic configuration, whereas 3p4 you have a paired orbital. When there is a paired orbital, we say it makes repulsive forces. So the reason why sulfur is lower than phosphorus, we say for phosphorus electron is removed from the half-filled stable p3 arrangement, whereas sulfur electron is removed from a paired orbital which has repulsive forces. So that's the reason why we say phosphorus required higher energy than sulfur to remove an electron. If I tell it again, for phosphorus electron is removed from a half-filled stable p3 arrangement, whereas for sulfur electron is removed from a paired orbital which has repulsive forces. So due to that reason, we say phosphorus has a higher first ionization energy than sulfur, right? So that is the reason why the ionization energy values of group 6 is lower than group 5, and earlier we discussed why group 3 is lower than group 2. So that is the main thing they have in the first ionization energy, right? Now when we come back to the next part, which is the successive ionization energy value, the successive ionization energy value, the idea is once one electron is removed, the next electron is removed after that. So first ionization energy of, let's say, sodium, it is like sodium gas goes to Na plus gas and P. Then second ionization energy of sodium is like sodium plus gas goes to sodium plus 2 gas. Likewise, we can write third ionization energy, it is sodium plus 2 gas goes to sodium plus 3 gas, like this. Now when you go about the successive ionization energy values, always successive ionization energy value keep increasing. There are two main reasons for that. One reason is electron is removed from a positively charged ion which has greater nuclear attraction. That's one reason. The second reason is when the positive charge increases, atomic or the ionic radius decreases, so electron is much closer to the nucleus, so it is hard to remove that electron as well. So those are the two common reasons why the successive ionization energy values are keep increasing. So always endothermic values, the values keep increasing. Now, when we talk about the successive ionization energy values, we would see a nice graph or a specific way that electrons being removed. The idea to remember is always if the electron is removed from a completely filled main energy level that requires very high ionization energy. So when it comes to sodium, as I am writing sodium, sodium has atomic number 11, which is 1s2, 2s2, 2p6, 3s1, right? Sodium 11, 3s1. So once the first electron of sodium is removed, that means after the first ionization energy, the second electron is removed from a completely filled p subshell, or we can say the second main energy level that requires very high energy. So I'll put a table as well so you can see the values. So first ionization energy to second ionization energy, there's a huge gap, almost 10 times higher than the first ionization energy. So what happened is, when you remove the second electron, that is removal of electron is 2p6, once we do that one, then we can remove electrons gradually because now it is in the same subshell. Again we would see a very high jump when the electron is removed from the first main energy level. So to draw the successive ionization energy graph, we can't use the actual values because you can see the actual values are so big. So what we do is we use the log ionization energy value to the y-axis. And here we can say ionization number. So we use the log ionization energy value. It's a very common question. Sometimes they ask, why do we use log ionization energy values when drawing the ionization energy graph? Right? So why do we use the log ionization energy value mainly? We use the log ionization energy value because then we can fit them into the scale. Right? We can fit them into the scale. So when we draw for sodium, you can see the first electron is removed, and then 1, 2, 3, 4, 5, 6, 7, 8. We can remove 8 electrons with a gradual increment or the almost the same type of issue, and then we have another jump over there. So that is for the second ionization energy. We have a first highest jump, and then we'll have a 10th ionization energy because the electron is removed from 1s. So this is something we can take from the successive ionization energy graph. So you will have the ionization energy values. We take the log values. So like the first ionization energy is log 496, like that. Okay, to draw the successive ionization energy graph. So by looking at the elements, right, we can predict how it would be. For example, let's say magnesium. Magnesium is 12. So 1s2, 2s2, 2p6, 3s2. So removal of 2 electrons from magnesium, log ionization energy is again. Removal of 2 electrons would be easy or almost the same. Then the third one only it start to jump. And then it goes like this. So for magnesium, we can say 2 electrons can easily be removed. The third electron only it increases dramatically. So the idea is, if the first dramatic increment is nth ionization energy, the group number is n minus 1. Right? That is something we have to remember. If the nth ionization energy has the dramatic increase, the group number is n minus 1. In that case, in this case, it is 2 because third one is the highest. So magnesium is in group 2. For sodium, you can see first one, the second one is the highest. So sodium is in group 1. So likewise, we can get the idea. Other than these stuff, what we can take from the successive ionization energy graph, we can tell them about the group number. That's what I told. We can tell them about how many periods are there, because number of levels is equal to the number of periods they have. And we can tell how many electrons are there as well. Right? So those are the things we can get the successive ionization energy graph. Sometimes you will get it as an MCQ. They would give the energy values like this: 625, 2811, then 5038, then like 12,756, then 15,766 like that. Then they have asked which one is the group belongs to. 1, 2, 3. This is the dramatic increase in starter, right? The dramatic increase is over there. So 1, 2, 3. Fourth one is the dramatic. So we say it is in group 3. Likewise, we can predict the group number from the successive ionization energy values. Right. Okay. So today we discussed the ionization energy values. We discussed what happens with the left to right of the period, top to bottom of the group. What is the difference between group 2 and 3? Why there is a difference between group 5 and 6? And then we discuss about the successive ionization energy values. So if this is helpful, give us a thumbs up and consider subscribing. Thanks for watching.